In this problem, we have two binary search trees, not just binary trees, but binary search trees. And what we have to do, we have to return a list where the elements will be all the elements of binary search tree 1 and all the elements of second tree. So if there are even duplicate values, it will be there. And it should be in the sorted order. So regarding binary search trees, you must know that when we do in-order traversal of binary search trees, then the elements are in the sorted order. So how can we do that? So let's say we have two binary search trees. Then in that case, what should be the result? We have total of 2, 2, 4, 6 plus 5, 11 elements. So smallest is this one. These are the two smallest. So smallest among these is 2. Then next is 3. Then next is one of these 4. And then the other 4. Then 5 we have. 6 we have, 7, 8, 9, 10, 12. 2, 4, 6, 8, 10, 11. So this should be the answer. So how we can do that? So one very straightaway solution would be that traverse the first tree in any order, not necessarily in order, pre-order, post-order, any order, just visit all the nodes and put it in a list, no matter what order. So 4, 9, 8, 7, 10, 12. And then put these in after that. So 2, 3, 4, 6, 5. Then sort this. So what should be the time complexity here? So you have to return this list anyway. So you are not using any extra space for that other than the required result. So here if we have m elements and in this we have n elements, then time taken will be m here, n here, followed by m plus n plus m plus n log m plus n. So this will dominate, this you can ignore. So this is the order time complexity. You can do some tweaks here. You can do it slightly better. So do it in order. So 4, 7, 8, 9, 10, 12. So first let's use the same list. There are multiple ways of solving it and you must have figured out a few ways. So this is in yellow and then we will write the content of second one in green. So 2, 3, 4, 5, 6. So this yellow and this green are already sorted since we have taken in-order traversal. Here if you are sorting the complete thing, which traversal you take does not matter because we are sorting it after all. Here also we will sort, but we know that if we do in-order traversal, this will be sorted. Similarly, this will be sorted. These two are from different trees and we are not using any extra space. This is the list that we want to return anyway. Now keep the pointer of first one for both of these. Whichever is smaller, push that ahead of this. So 2 comes here and it disappears from here and then increment the pointer. Again compare, 3 is smaller, so push 3 here after this. So this does not help much since if this is some array kind of container and in C++ I guess you have to return a vector. So inserting in between and then shifting everything, that's O of n. So it may even reduce the time complexity, increase the time complexity to n square, that is m plus n square. So it does not help. But you can use this the same thing, that is keep 2 separate lists. So keep 2 temporary lists. And then what we will do? We will do the idea similar to merge sort. So we have 2 lists, we have to merge them into one. So we have 2 pointers, one here, one here. This is initially empty vector, or you can, if you know the size, you can initialize with that size. 2 is smaller, so insert 2 here. We are just pushing back, so it's constant time. Then we compare with 3 and 4. 3 is here, then we compare 4 and 4, anyone. Then 7 and 4, 4, 5, 5 and 7, 5, 6 and 7, 7. 6. And then this is empty. Then put 7, 8, 9, 10, 12. And this is the answer. So what is the time complexity here? So to get these two, we took m plus n. We did traversals and then merging would take another m plus n time. So overall time complexity will be m plus n. But here we have two spaces. One is for this result. So in any case, you have to use a space of m plus n since you have to return this list. But here we used two extra spaces also. So this should also work fine. It's simple to understand, and you should try this. We will go one step further, and instead of using two complete size vectors, so in this case we will definitely use m plus n space, because the size of this first vector will be m, size of the second vector will be n. So slight improvement we can do is that we can do it in one pass. That is, while doing the Inorder traversal itself, we keep a stack. So here we will do Inorder traversal using stack and not recursion. So just let's briefly recap how to do Inorder traversal of a tree without recursion. So we keep a stack, we push root into the stack, so 10 is here, and then keep going left. Update the current pointer. So current is here, we have inserted current, and then current becomes its left. So you come here and again insert the current, and current comes here, always left. So we insert 4 and current is its left. So current is now, current will become null. So we stop. When we stop, what we do? We pop this top element. So 4 is here. And whatever we have popped, current becomes its right. But its right is empty. So nothing will be pushed here. So now this is the stack. Again we pop it, 7. And whatever you have popped, push its right. So we pushed its right, that is 8. These two are gone now. And again repeat the same process, that is keep going left until current is null. So current is here, we pushed it, current is here, we pushed it, current becomes null. So we pop it. Okay, so some inconsistency here, because we have made 9 as the left of 8, which is invalid. It should be, this should be 9 and this should be 8. The tree was drawn wrong, so when we came here we would have pushed 9 here instead of 8, and then 8, and now current is null, so 8 is here, this is gone, then 9, none of them have right child, so we can keep popping. 9 is also popped, then we pop 10, and then we push its right, that is 12, and then current comes here and we try to go left, but it's null, so we pop 12. Now its right is also null and we are done. So this is the way we do Inorder traversal using stack. So stack will not be always containing all the elements. It will contain at max this kind of depth of the tree. So here what optimization we can make, instead of using two complete size vectors, additional spaces, we can have two stacks, S1 and S2, and then do Inorder traversal for both of these. So remember, we keep going left, keep pushing to the stack until current becomes null, and we are always making current equal to its left. So we come here, here, now it's null. Similarly here, here, now it's null. So let's run through this example again. So we have two stacks and these all are wrong. This is 9, this is 8, S1, S2. So S1 is for tree 1. So it has 10, 7, 4. Now we will stop since current has become null if we make it left. And S2 we will have 5, 3, 2. So here we will stop and then compare their top values, which is smaller. So clearly 2 is smaller. So 2 is popped and we look at its right is null. So we will not insert anything, go to 3. And then pop 3. Or rather compare first, because here we have two stacks. So again 3 is smaller. We pop 3 and push its right. Again, so this is done. Again compare the two. 4 is smaller. Let's say this time we picked this one. So 4 we popped. We removed from here. Its right is null. So we come here. Now again we compare 7 and 4. This 4. So this is also popped and we go back to 5. Next comparison will be from 7 and 5. So we will pick 5 Then 5 is popped and we insert its right, that is 6. And here we compare 6 and 7. So 6 is printed and we pop it. Its right is null, its left is null. This is done. Then we have 7 here. So we pop 7 and push its right. 7 is here, its right is 9. And keep going left. That is push 8 also. Now we will stop. Now we will compare against this, but this is already empty. So no need to compare, just the normal in-order traversal process. 8, its right is null, nothing to push here. Then we pop 9, its right is also null, nothing to push here. So next one is 10, just 10 is in the stack. So we pop it and then push its right, that is 12. Next we try to go left, but it's nothing is there, so we pop 12 and we are done. So this is the list. So here at a given time the stack was holding at max 3 elements. So that will be proportional to depth of the tree. So here the space will be of the order of h1 plus h2. You can take the maximum worst case depth. So from m plus n to h1 plus n2. But again, this is not that important. You will anyway be returning a list of size m plus n. This was just slight optimization and making the algorithm a bit more elegant. So let's implement this last approach. So before that, I would highly recommend that you just take a small binary tree, no matter it's binary tree or binary search tree, and try to do in-order traversal of that tree using stack. And once you are comfortable writing that, then try to implement this this method. That should be simpler for you. So let's begin. So these are a few examples, nothing special here. So tree node pointer, and we have stacks s1, s2, then the result vector. Root 1 and root 2 are the roots of the two trees. So if while root 1 is there, or root 2 is there, or s1 is not empty, or s2 is not empty, we will continue so that we put all the elements in the result and don't miss out anything. So first process the root 1. So while root 1, so this will act as the current that we were talking, current node for the tree 1. S1 dot push root 1, and root 1 equal to root 1 left. So this will stop when left is null. So this will be the minimum in first tree at this state when this while loop ends. Similarly, for root 2. Now this root 2 will be the minimum. The top of the stack will be the minimum in the root tree, which we have not inserted in result. Then there are a few scenarios. Either S2 is empty. If S2 is empty, then we pop only from S1. Or there is another case where we will pop from S1, which is S1 is not empty, and S1 dot top dot val. So this top will return a node pointer. So in order to get the value, we need to use this val. So when S2 is empty, this part will not be executed. So this part is executed only when S2 is not empty, and S1 is not empty, we are adding anyway. So this case is for the case where both S1 and S2 are non-empty. Then we will compare their top values. But if one of them is empty, then just pick from the second one, and we will write an equivalent case, equivalent opposite case. That is, S1 is empty, then pick everything from S2, or if both are there, and the other case. So we have tried to combine it intelligently, so that if S2 is empty, where you will pick, you will always pop from S1. Or the second scenario is that both are non-empty. So S2 is not empty and S1 is not empty. And S1 is smaller. The top of S1 is smaller. So in both these scenarios, we will only pick from S1. So root 1 equal to S1 dot top. And then pop it. And we will have exact opposite scenario of this, where we will pop from S2. So that will be the scenario where either S1 is empty. So if S1 is empty, you will always pop from S2, or both are non-empty and S2 top is smaller. Okay, so line 17. And the solution is accepted, and we are right here around 96% of the accepted submissions. So you can see we have surpassed the 2 peaks. So main distribution is in this part, and it's highly distributed, but we are on the safer side. So let's rewrite this in Java and Python. So here pop also returns the top of the stack, so no need to call top separately. And this works, so submit. Solution is accepted, and here also it's around 82% of the submissions. Next we will write this in Python 3. So -1 means last element that we have appended in this list. So it's acting as a stack. And the Python solution is also accepted.